Okay, hopefully still fresh is the concept of these oxidation numbers that we are assigning to various, let's say, atoms, constituents of our chemical reaction. Okay. Let's take, for example, what if they're non-ionic? We said what we do is we take the most electronegative, okay, and we say that becomes the ion for itself, right? So let us take, here's a couple. Let's just do a few, all right? It would help if I did that right. CH4, good old methane, all right? Let's just have a look at methane. What do we do? Well, carbon is the one, it's more electronegative than hydrogen, isn't it? So what do? We say, right, carbon, you become your ion. We say, right, you are a nonmetal, we are going to then make you a -4. Hydrogen, right, we know is a +1, okay? So what have we got? We've got the carbon, the hydrogen, therefore, has to be equal to +4. There's no charge around this here. It's not an ion. So the sum total of those two must be equal to 0. So therefore, obviously the hydrogen must be a +1. Okay? This 99% of the time the hydrogen's a 1, because why? Hydrogen's only got one electron to get rid of. You'll see in a few moments when we do something. It's only got one. Okay? It can't lose more than that one, can it? Because it's only got the one that it can give away to somebody or to share with somebody. All right? Let's take a look at what about H2O? Let's have a look at H2O. Right? We say, which is the most electronegative? Oxygen. Oxygen is a -2. Therefore, we say, right, I'm going to work with a -2. Do I have a charge on the outside? No. Therefore, my hydrogen over here, let's just do it mathematically. 2 times x, okay, -2, must be equal to 0 because there's no charge. Therefore, 2x is equal to 2, x is equal to +1, and hey, we know hydrogen is a +1, right? It's only got the one to give. We're going to look at an odd one, the peroxide in a second, okay? What about CO2, okay? What about CO2? Now here, which is the most electronegative? The O, isn't it? So we work with him first. We say, you become a -2, don't you? So therefore, I have got 2 of you. So my total, my oxidation number up there is going to be -4. Therefore, x -4 equals 0. Therefore, x is going to be equal to +4. Can you see? There's the situation, right? The carbon in methane, okay, -4. The carbon in this one was a +4 because of the difference in electronegativity, right? Does that make sense? I hope. Essentially, we're saying that here in this case, in CO2, the oxygen has taken the electrons away from the carbon, hasn't it? That's the basic thing of the electronegativity, right? Let's have a look at what about okay, what about an ion? What about OH minus? All right, oxygen is the most electronegative, isn't it? So we start with oxygen. So right, what are you? You are a -2. Okay. Therefore, now we've got to look and we say, okay, -2, and then the hydrogen, let's call it X. But now we've got a charge on the outside. So that must be equal to -1, isn't it? So therefore, in this situation here, let's take it across. X must be equal to, that goes across, +1, right? Because if this is a -2, let's do the maths on top. If this is -2 and I +1, what do we end up with? We end up with a charge of -1, which is the charge on the ion itself. Because the oxidation number of the ion itself is the charge on the ion is the oxidation number. Okay? Let's look at another one. Bisulfite. Now you say, okay, HSO3 minus. Okay? Now we're going to assign oxidation numbers to this. Can you see, I mean, I know that I'm pretty sure that in grade 10, when you were given that list of ions that you had to learn, and with all my students, I've said, please guys, just learn it, make sure you know it. It's critically important as it forms really a lot of the building blocks that you're seeing now, doesn't it? They're coming back, and they're going to keep coming back. So those ions, if you don't feel you're strong enough on them, my recommendation would actually be go back and refresh yourself on that little table. Okay? If you can't find the table or whatever, it's not in your book currently, or last year's book or wherever, you can always go on and download the common ions from the internet. There's dozens of sites that have got them, right? And you'll quickly see the ones that you're familiar with, right? Now, the reason that I'm saying that is because knowing the ions and the charges on them saves you a lot of time. It really does. Okay? You don't have to worry about making the mistakes. You don't have to be afraid that in essence what you've got is a wrong charge, right? Because all the oxidation numbers are relating to that charge on the ion themselves, isn't it? What about this bisulfite ion, HSO3? Well, how do we deal with these? Well, first of all, the overall charge on this is going to be equal to -1. You can see that that is an H plus, an S, and an O3. So let us just separate them out. Just for workspace. Okay? Now we say, right, the most electronegative of all of these, and you can look it up and you'll see it's oxygen. So I'm going to start with you. Therefore, oxygen becomes -2. That's the negative one. That's where we're starting. So oxygen -2. And I must multiply because there's 3 of them. So we end up with a -6 at the top. Okay. Now, well then, because oxygen was 3.5. And the sulfur was 2.5, I think it was. All right? I can't check that right now. Well, you guys can check it on your periodic tables. Okay? 2.5 or 2.1, not 100% sure. Okay? Basically, I can't read my writing over there. 3.5 to 2.5. Okay? So the oxygen is the one we start with. So we've got a -6 at the top there. Okay? So what happens now? We say, okay. Now remembering that on the outside of all of this lot, okay, we have a -1 charge. Right? There. That's it there, right? Can you see I've split them up? I found the most electronegative one. Then I say, okie dokes, hydrogen, okay, I know is a +1. That's all it can give. So we make this a +1 over here. So if we do it mathematically, we can say that x +1 -6, can you see I've just basically added that, must be equal to -1, which is the charge on the ion itself. So what do I get? We say that then x is going to be equal to 6 +1 goes across -1. So it becomes, the 6 goes across and it becomes a plus -2, which is going to be equal to 4, I think, if I've got it correct. Okay? And it's a +4, right? So x is going to be +4. Let's check. 4 + 1 is +5. -1 -1, that agrees with the charge on the outside. So in this case, the sulfur has an oxidation number that we have to work out, and we assign it to the sulfur as a +4. Right? Let's just go over that again, shall we? What do? We split them apart so that we can have some space to work. We then put the bracket around them with our ion on the outside. Okay? I'm going to do H2SO4 as well. So we put the ion on the outside. It had a -1 charge. The next, we look at which one is the most electronegative. Hydrogen obviously isn't. So we're looking at the nonmetals in this case. Oxygen is 3.5, sulfur 2.5. Therefore, the oxygen forms its valency ion. It's -2, okay? Therefore, we say, right, hydrogen is a +1, the oxygen is 3 times -2 because we've got 3 atoms. Remember, each oxygen becomes a -2. So we've got 3 of them. So we've got -6 on top, 3 times -2. Then we solve for it and we say, right, the sulfur is the one we don't know. So we call it X. And then sum the top. It's a bit like an exponential equation, isn't it? Once we've got the top, we can then solve for the X across the top. So we say that X plus 1 minus 6, that's summing the top row here, must be equal to the ion on the outside, which is the -1. All right? And we solve for X. So sulfur in this one had an oxidation number of +4. Okay. Well, then let's have a look at what about H2SO4, okay, which is sulfuric acid, isn't it? H2SO4. Now let's have a look. Well, once again, obviously it's the oxygen's got the most electronegativity. So what I'm going to do is I'm going to start there. I'm going to say this is now 4 times -2. 4 there, -2 is -8. So on top, I go to -8. Hydrogen, H2, so that's +2. Can you see what we've done? Now, let's say, therefore, if I sum across the top, I must say that +2 plus X minus 8 must be 0, because there's no charge on it. It's not an ion. It's now a compound, and it's chargeless, so it must be equal to 0. So what do? Well, let's rearrange it. X is going to be equal to 8 minus 2 is going to be equal to 6. So can you see that what has happened here is that in going from the bisulfite, the HSO3, to H2SO4, right, you can see that the sulfur's oxidation number has changed. That's an indication of either gaining or losing electrons in this process, isn't it? All right. Let's now have a look at something slightly different. All right. Yes, let's have a look at this one because it is an anomaly, right? And it very often comes up in a test or an exam just because it is an anomaly. What about this one over here? Sorry, guys, let me just go back to start off with the black one. We say H2O2. Okay? Hydrogen peroxide. Okay? We say, all right, let's go through our rules. We say O2, you must be, O is a -2 times 2 of you. So I've got a -4. So there's a -4 there, which means that hydrogen, 2 times X must be -4. So 2X equals 4. So X must be equal to 2. Right? But it can't, because hydrogen has only got, it's only got 1. So it can't give off 2 electrons, can it? It can only give off 1 electron. So what actually happens over there is really, it says, okay, in this case, hydrogen rules the roost. We say, but sorry, can't do. So let's go back to the building blocks and start with hydrogen. Okay, let's say H2O2. Hydrogen's the limit, if you like, it's like a limiting reactant, isn't it? Really. Hydrogen's only got. So we say, right, my oxidation number there is 2 times +1, which is +2. Therefore, right, 2x, 2 times oxygens, we say is going to be equal to 2x plus 2 must be 0. Agreed? Therefore, 2x must be -2. X is -1. So the oxidation number in this case of O is going to be -1, and the other one is a -1. Just let me tidy that up. Over there, it's a -1. What has happened? essentially hydrogen and hydrogen, he's only got one electron to give. So what does he do? He hands one electron over to the oxygen, right? The oxygen, under normal oxidation number conditions, would have been the most electronegative. So the oxygen would have been a -2, wouldn't it? Remember? That's where we started off. We said you are -2 times 2, right? But now in this case, hydrogen's only got one. So the oxidation number actually is changed to a -1. All right? Let's say that's the odd one out that we have to look after and look for. All right? Same kind of thing when in thingies when you're looking at and I'm sure you've done that before when you're looking at series, right? You start looking for things like 1, 1, the x and the y, 1 and 1, 2 and 4, 3 and 9, and you know it's the square, right? So it's just looking out for some of the anomalies that we can do. All right. Now let's consider this one. We've been given an ion, okay, MnO4 minus. Now we want to, let's say this is going to react in some way or another, so we need to assign oxidation numbers to it. Okay, what do? Oxygen is the most thingy, so we say, right, Mn, split them apart like that. Sorry, I always write my N as a capital there. I know I shouldn't. Okay, and we say, right, on the outside we've got a -1, which is that, correct? So we've split them so that we can work. Most electronegative, oxygen. Oxygen goes to its valency of -2. Then we multiply it because we've got 4 of them. So you can see over here that that is a -8. Okay? So we say, all right, manganese, let's call it X. Okay? So therefore X plus -8 must be equal to -1. This is my outside charge because it has one. Okay? Is -1. So therefore, X minus 8 is going to be equal to -1. X in this case is going to be, take it across, and it's going to be 7. So what are we saying? We're saying that the oxidation number that we are assigning here is a 7. All right? Well, that means that in this process, the manganese and the oxygen, the manganese has actually given away 7 electrons, right? Because essentially it's got a +7, correct? That's the charge. That's the charge on the manganese. Really, what we've got is we've got this. It is Mn plus 7, correct? So it's given away 7 electrons. You say, but hold on, that's a lot to give away. We're only normally used to things like Al plus 3, B plus 3. We're only really there. I mean, carbon is the one that's the 4, the plus or the -4, depending on what it's bonding with the O's, or the carbon tetrachloride, carbon tetrafluoride, those kind of things. The more electronegativity will change the carbon to a positive, bonding with, say, for example, hydrogen, organic chemistry, the carbon becomes a negative because we've got 4 H pluses. Well, manganese +7, not numbers that we've seen before. What is important with this is to say, but hold on, if you look at it, how many electrons has manganese got? If you go to your periodic table and look up the manganese element number, you'll see that it is actually 25, all right? So theoretically, it's got 25 electrons that it can give away, all right? So if you want to take it just a bit further, if it is in fact 25, all right, we've got, let's see if we can work it out, 1s2, 2s2, 2p6, 3s2, 3p6. Let's have a look where we are. There's 10, there's 18, 3p6, 4s2, okay, because the 4s fills before the 3d, all right, and then 3d we've got here, 10, 18, 20, and 5. Okay, just check 10, 18, 25. So that's where we are, right? So if you look at it, what can we've said it's given away 7, essentially, all right, we would say there they are, isn't it? The 5 of there and that. So it's dropped back to the 3p6 lower down. All right. Once again, it's all tying together with the previous elements of this. Right? So the oxidation number concept, how do we do it? Well, we apply a straightforward set of rules, don't we? We apply a straightforward set of rules. We say to ourselves, okie dokes, element, we give it an oxidation number of 0 because it's got no charge. If it's an ion, it gets the oxidation number of that. If it's a polyatomic ion, the sum of all the oxidation numbers of the constituents of the polyatomic ion must be equal to the charge on the ion itself. Let's take another example. How about, let's take PO4, phosphate. PO4 minus 3. Well, let's ask what is the oxidation number of P in this whole thing? Well, first of all we say, right, PO4, I split them up and I say there's a minus 3. This is the most electronegativity, so it's going to go to a minus 2. Multiply it by 4, minus 8. Minus 8 is there. Therefore, now we say x minus 3. Sorry, my bad. X minus 8. Let's just make that tidier. X minus 8 is equal minus 3. Therefore, x is going to be 8 minus 3, which is going to be 5. So the oxidation number of P is 5 plus 5. Right? So once again, it's got 5 that it can give away. Okay, I'm going to go and put it into the ionic, or rather the electron configuration. But you can see that these things are actually not that difficult to work with, are they? Let's take an example, all right, and just use an oxidation number in an example here, shall we? Right, I want to put hydrogen gas plus Cl2 gas goes to 2HCl, let's say, in a gaseous format. Okay, let's now assign oxidation numbers. Well, what are the oxidation numbers of hydrogen? 0, because it's an element, isn't it? It's H2. So let's give it an oxidation number of 0. Chlorine, also an oxidation number of 0. Okay, it's got an oxidation number of 0. Now let's have a look. What would the oxidation number be of here? Well, chlorine, most electronegativity. So chlorine, I'd start with you, and I'd say minus 1. I've only got one of you at this point, so I say you're a minus 1. Hydrogen is a plus 1. Correct? So can you see that my chlorine, let's just go and say the chlorine, okay, has gone, it has decreased, hasn't it? How does it become negative? It gets an electron, doesn't it? And Rig reduction is gain, oil rig, right? And yeah, let's just check it properly. But you know what's coming. I'm just going to take it down this side just for a bit of tidiness. Whoops, sorry, I went a bit far. Let's put you there. Here we've gone from 0 to 1, so we've increased the oxidation number. Okay, and it's lost, hasn't it? It's actually increased, means losing electrons. So it's lost electrons Therefore, oil oxidation is loss. Okay? Reduction is gain. Oxidation is loss. Okay? Key that we actually go through these processes, okay, and understand them. Because it means so much more if we understand what we're doing than just a recipe, because this is a lot of the work that's going to be going forward using this, okay, the whole electrochemistry concept. All right, and there's quite a lot of stuff to go through there, because a lot of it, as I say, is we're going to be discussing endothermic, exothermic reactions using this these electron transfers. We're going to be using tables of half reactions to predict voltages of these reactions, okay? Because you can see that in some of them, because there's a flow, because there's a transfer of electrons, right? What does it actually mean? Let's just stop and ask ourselves. You can see that in this case here, we are getting a bit ahead of ourselves, but let's just discuss it for a second. What have we got? We've got a transfer of electrons, correct? Let's go and back up and say, yes, in this reaction at the top here, we transferred electrons, didn't we? Because we had the reduction and the oxidation, we lost and we gained, right? Now, what does that mean? It means this, doesn't it? Okay? It means that we are able, if we are transferring electrons, right? Those electrons must be flowing. Okay? What is electrons flowing? Well, it's an electric current, isn't it? So this whole process is leading us towards that if we've got these reactions that are causing electrons to flow, essentially we're creating an electric current from these chemicals, aren't we? That's something that we're going to go into in a little bit. Okay? The next one I'm going to do is we're going to look at some half reactions, some balancing out using acidic, alkaline mediums and water, all right, which is pretty much at the complex end of this whole process, all right? And then we'll do those examples like that. Then we'll go a little bit into the half reaction tables and discuss some of the concepts in there.